Okay, hi everybody. Explain what the geometric definition of sine theta and cos theta has to do with e to the I theta, and how e to the I theta leads to computable formulas for these things, right? Because nobody knows how to compute the cosine of 1.1. Actually, probably nobody knows how to compute the cosine of 1. So until we learn this, let's do it. And this is a great reason for the complex numbers. Okay? That is a great reason. In fact, in quantum mechanics and all the things that we use complex numbers for, it quite often has to do with circular motion. Things that are circling around or things that are periodic. That means they have circular symmetry. And that's why we can use complex numbers with Fourier series and Fourier analysis and signal, and we can use the EQ on our stereo to do all these things. Are complex numbers, periodic, circular, everything. So we should really know this, and it's all about e to the I theta. Okay, so first the geometric definition of sine and cosine. So sine theta is adjacent over hypotenuse, and cos theta is what? No, whoops. This is the opposite over hypotenuse, and this is the adjacent over hypotenuse. And what does this mean? I mean, like if you have some triangle that has 90 degrees, and you pick one of them and you call it theta, and you say this is an angle theta, and nobody knows what you mean. But actually what you mean is that if this triangle were embedded in a unit circle, then this arc length, this circular arc length, has length theta, which is theta, meaning theta is a real number. It is a length of a circular arc. And so I guess sort of for us, especially because we are going to use e to the I theta, we should just note that what are these things? So if we have a circle and we have some point on the circle, then the x-coordinate will be cosine of theta, and the y-coordinate will be sine of theta. But where's theta? Well, theta is this arc length. That is theta. It is a real number. Okay. And then, this is this piece right here is cosine of theta, and this piece right here, the length of it is the sine of theta. Now this is a geometric definition. A geometric definition is great, but not for computing. Not for computing anything. What is the cosine of 1? Nobody knows. They know how to roughly draw it, but nobody knows how to calculate it. So let's compute. Okay. Now, this just says explain what it has to do with e to the I theta, and so I'm not going to prove it yet. We'll do that next video. But first, let's just say that consider the curve. So here's the deal. We're going to take a real number, we're going to call it theta, and we're going to map it into the plane. Well, what is the plane? Well, it's just the complex numbers. And so what number? Where should we send theta to? Well, we'll send it to e to the I theta, where what we mean is, actually, we're going to send it to this. The limit of the sequence of partial sums of this formula, this power series, is the point in the plane that we're going to send theta to. This gives a curve in the plane. So consider the curve. And what are we going to claim here? So the claim this curve wraps around a unit circle at, and this is crucial, at speed 1 at unit speed. It goes around a unit circle at unit speed. Maybe I even say that just because it sounds nice. A unit circle at unit speed 1. Meaning, what does this mean? Meaning that e to the I theta is exactly this point. Right there. Okay? It's going at unit speed, wrapping around and around and around and around. And so after time theta, we have reached exactly this number. But okay, why is that important for us? Well, then, if that's true, so I'm even going to say that because we have not proved that yet. If that is true, if that is true, then the cosine of theta is just the real part of this number, of this complex number. Because the real part is just this horizontal coordinate, that is the cosine. Okay, right there, that's the cosine, that length. Right, so, and sine theta is the imaginary part of this number. And this gives really nice formulas. It turns out that if we look at this series, what we'll get is that cosine of theta is 1 minus theta squared over 2 plus theta to the 4th over 4 factorial minus theta to the 6 over 6 factorial plus blah, 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 blah equals theta minus theta to the 3rd. The sine theta is now this plus theta to the 5th over 5 factorial minus theta over 7 over 7 factorial, blah, 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 blah. And that's just going to come from the formula for e to the I theta. Since e to the I theta is, by definition, 1 plus I theta squared over 2 plus I theta to the 3rd over 3 factorial plus I theta to the 4th over 4 factorial plus I theta to the 5th over 5 factorial plus dot, 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 dot. And let's just look at what this will be. Well, let's collect all the real parts. So this I squared will be minus 1. So we'll get this I to the 4th will be just 1 again. I to the 4th is 1. And I to the 6th, I theta to the 6 over 6 factorial will be, well, I to the 6 will be minus 1. Yeah. And so this will be the all the real parts that where the I becomes either minus 1, like here and here, or plus 1 when you take I to an even power. And then the odd parts will either be I or minus I, and those will be, I guess, I'll say plus I times, and here we get a theta from this one. And then here will be an I, but it'll be a minus I, so there'll be a minus theta to the 3rd over 3 factorial. Here will be an I, but it'll be a plus I, and etc., etc. So you see that exactly the real and imaginary parts will give these formulas. And that's how we can compute. That's amazing. So, I mean, the only thing we need to do is prove this. We need to prove that this curve, this is a curve in the plane. You know, every number of theta will be some limit of a sequence of partial sums. We know that this is absolutely convergent for any complex number, so certainly for I times theta, it'll converge. It converges for anything, if you put anything here. Oh, this should be like that. There we go. That was wrong. Okay, I theta, you have to plug in I theta. You know, x to the n over n factorial is the formula, and so we're plugging in this complex number. Okay, and so this is some formula, like for example, 0 would go to 1, because this starts off with something to the 0 is just 1, and then we're going to have I theta to the 1 plus I theta squared over 2 plus I theta to the third over 3 factorial, etc. And all these, when you plug in theta equals 0, all these go to 0, and then you just get a 1. Okay, so anyway, you can plug in other numbers. You can plug in 0.5, and you'll get some complex number. Okay, so this curve, if we can prove that it wraps around a unit circle at unit speed, then we have connected to the geometry. And that is how the complex numbers are useful. They have everything to do with circular motion. They have everything to do with periodic motion, periodic signals, repeating patterns, because they have circular, just the circles are just built into the complex numbers. And this is a great example of that. Okay? That means we can actually compute things. Okay, so consider this curve. We need to prove this. Let's do that next video. Let's prove that this curve wraps around a unit circle at unit speed. And then we have these great formulas for the cosine and sine right here. Computable formulas. Okay. That's all for this video. Let's prove this in the next video.